Hello. Today we'll discuss integrator drift and its effect on satellite orbit simulator error. Then I'll show you how to test SOS for these errors. I think you'll be surprised by the accuracy of our simple numerical integrator. In the image I show on my right, you see the mathematical flowchart of the spacecraft's equation of motion, which must be solved to simulate a near-Earth satellite's orbit. Here, the total acceleration felt by the spacecraft is the summation of Earth's gravitational acceleration plus several acceleration perturbations, such as those due to the Moon and Sun, Earth bulge, Earth atmosphere, thrust, and solar radiation. Note that two integrators must be used to solve for spacecraft position, R. First, we integrate total acceleration as a function of time to get velocity, and then integrate the velocity as a function of time to find position. Then, this new position is used to find the new acceleration due to Earth gravity. We then increment the time step and repeat until the final simulation time duration is reached. Of course, some of the gravity perturbations are also a function of spacecraft position, but showing these in the image would unnecessarily complicate the flowchart. Integration is simply repeated summation. To produce zero error on the output, the time step would need to be infinitely small, resulting in an infinite number of integrations. Since this is not practical with digital computers, we use a time step that is small enough to reduce errors to an acceptable level, but large enough to keep the calculation time short. In SOS, our default time step is 1 second. Therefore, a 100-day simulation will require 8,640,000 summations for each integrator. Modern personal computers can do this in less than 10 seconds. Unfortunately, since the integrator output is used to calculate the integrator input for the next loop, integrator errors accumulate over time. Therefore, our integrator error test simulation must run as long as possible to see the incremental error. The simulation duration limit for SOS is 1 second less than 100 days. To isolate the integrator error from other sources of error, we remove all acceleration perturbations, resulting in the following mathematical flowchart where only Earth gravity is considered. Note that acceleration is represented by R with 2 dots over it, and velocity is represented by R with a single dot over it. This represents a perfectly spherical Earth with no atmosphere. Also, there is no thrust and no gravitation forces due to the Moon or Sun. Finally, there is no force due to solar radiation. Now open the ISS orbit example project file, which I've already done. First, set the simulation time span to 99 days, 23 hours, 59 minutes, and 59 seconds. Then press the Tab key. Next, remove all sources of gravity perturbations by unchecking these checkboxes. 1. Earth bulge and atmosphere in the Earth group box. 2. Moon gravity in the Moon group box. 3. Sun gravity in the Sun group box. 4. Solar radiation in the satellite group box. Finally, uncheck the satellite orbit steps checkbox in the display group box. Now, recalculate the simulation. If there are significant integrator errors in the simulation, you will see drift in the orbit position as time progresses. Zoom in to look closer. The orbit drift is so small that you cannot see it. In fact, the orbit has drifted by only 12 meters. This demonstrates that the SOS numerical integrator is both fast and accurate. To convince you that this simulation time is in fact 100 days, run the simulation at high speed. You may also want to turn on the ground track. We hope you found this video useful. If so, please give it a like. If you want to be notified when we add more videos, click on the notification bell. Finally, leave a note if you have comments or requests for new videos. Goodbye.